All right, AP Chemistry. This is your day 50 assignment. It's on Hess's Law, Enthalpy of Formation, and bond energies. This week we've been talking about intermolecular forces, and we're really done with that topic. You really just had one fairly long assignment on that, and to watch the video involved in that. This goes back to last week and thermochemistry. So this studies heat that goes in and out of a chemical reaction. Okay, so let's get started on this. So that is actually the first question. What does thermochemistry study? It studies the energy. We want to say more generally energy. Okay, so thermochemistry studies energy that enters, that's endothermic, or exits, exothermic, a chemical reaction by measuring the enthalpy, which is the heat. All right, so we want to know how to solve four types of problems with regard to this. Okay, so what are the four ways to compute heat? The first one is calorimetry, which we did do last week. Okay, so the first one is calorimetry. That's either constant pressure, which is called coffee cup calorimetry. That's less heat, less volatile, less explosive. And constant volume, that's bomb calorimetry. That's done in a very sturdy container because there is literally a combustion or an explosion going off in there that's releasing a whole lot of heat. Okay, the next one that we're going to study, just check this, I want to do them in the order, is enthalpy of formation. So we haven't talked about that one yet. Now these are all in your notes, in the notes for this unit, and those notes are included in this lesson from last week for thermochemistry. Okay, so these last three are the ones we're going to study today: enthalpy of formation, Hess's law, and bond energy. So those are the four methods for computing energy. You should be adept at doing any of those four. Okay, we will not do calorimetry today. All right, let's go down and answer some of these questions. What is the definition of heat, enthalpy of formation, HF, and how many moles of the product are shown in an enthalpy of formation formula? Okay, so Alright, so enthalpy of formation is the change in enthalpy that occurs when 1 mole of a compound is created from its basic elements in their most stable form. Alright, so let's go ahead and look at this. Let's look at this first one. So we're forming CH4. So in order to form CH4, we need 1 mole of carbon, because there's 1 mole of carbon in CH4, and we need 4 moles of hydrogen. But we don't put 4H atoms because hydrogen atom is not the most stable form of hydrogen. We talked about hydrogen being one of the 7 diatomic molecules. In its most stable form, hydrogen appears as an H2 molecule. So you don't put 4H here, you put 2H2 because that's the most stable form of hydrogen. Okay. Another thing is this, what's the most stable form of carbon? And you're not going to have to know a lot of these, but here's one that you should know. The most stable form of carbon is graphite. It's actually what your pencil writes with. What the pencil I'm writing with right now is graphite. It's not lead. People say it's lead. It's not lead. It's graphite. And even though it's very soft, it allows us to write on paper, it is the most stable form of carbon. By contrast, diamonds, which are the hardest substance on Earth, are less stable than graphite, believe it or not. Over millions of years, a diamond will degenerate down basically into graphite. So graphite is more stable than diamond. You don't, as I say, you don't have to know a lot of those, but that's one you should know, that the most stable form of carbon is graphite. And you should know the 7 diatomic molecules, H2, O2, N2, F2, Cl2, Br2, I2, and F2. I think I said all 7 of them there. And that's those you should know. Those are back in the foundations unit, is knowing those, all right? So we'll go ahead and do that. So that's the definition of enthalpy of formation. It's how much heat is taken in or given off when 1 mole of a compound is created from its most basic elements in their most stable form. Okay, let's do the rest of these here. H2O. So what you're going to need is H2, and in its most stable form, it's a gas. Again, it's not just H, it's H2. All right, then you're going to need O2. And remember, we're trying to create 1 mole of H2O. Okay, now there's a little bit of a problem here. We've seen the balanced equation for creating water a number of times. I'm going to go up here and write it again. What it normally is 2H2 plus O2 will give us 2H2O. That's the balanced equation for creating water. The problem is that's 2 moles of water, and this definition says it has to be 1 mole of water. So what do we have to do? We have to divide everything by 2 up here. So that's going to give us H2 plus 1/2 O2 will give us 1 mole of H2O. Okay, so there's an implied 1 right there. This is about the only time in chemistry. I won't say the only, but there's not many others there's none that I can think of right now. The only time you're going to have a fractional coefficient, that you're allowed to have it. In fact, you have to have it because you have to show this for 1 mole of water, not for normally the way you would write the equation for 2 moles of water. Okay? So that's going to be a 1/2 right down here as well. All right? Again, it's the only time, certainly in this class, that you're going to have a fractional coefficient right there. Okay? All right. Let's go to H2O. Okay, and what I should have put is we're creating H2o Liquid. So that's an L right there. Yeah, I'll write it as a capital L, but it's lowercase, and it's usually scripted. Okay, so to create H2o Liquid. Now what about H2o Gas? You go ahead and write that for H2o Gas. It's the same thing, okay? All right, how about CO2? Okay, so you have carbon in solid form. And just to make the note of it, that's graphite. And oxygen in its most stable form is a gas. It's a diatomic molecule and it's a gas. Okay, so there you go for that one. All right, think about this one. C2H6. Again, it's going to be carbon in its most stable form, which is carbon solid. You don't have to write the word graphite every time, but just know that it is. And then you need 6 hydrogen, which means since hydrogen always appears as a diatomic molecule, it means you need 3 H2. And it's always a gas in its most stable form. So 3 H2 gives you the 6 that you're going to need. And this is ethane, so this is going to be... go ahead and C2H6, and it is a gas. Okay. So the intermolecular forces in this are not strong enough to pull it together into a liquid because it doesn't have very many atoms, and therefore it has weak London dispersion forces. I'm going back to the intermolecular forces unit, just making a point. So C2H6 appears as a gas. Its most stable form is as a gas. The same is true for C3H8. I want you to do this one on your own. Ones I'm circling, you do on your own. And we'll go ahead and do C4H10 together. Okay, I think you can do that one on your own too. So you do these three. They're exactly like this, except you got to make the numbers add up to whatever these are. Okay? All right. So let's go ahead now and answer a couple questions. What do the enthalpies in the table above generally tell you about the energy in a reaction system when a chemical compound is formed? Well, they're all negative, which means energy is going out. When energy goes out, that means the product is left with less energy than the individual atoms or molecules had before. And what that means is it's in a more stable form. It's more stable in this form, lower energy than it was when it was individual atoms, okay? So what it means is the compound, that's the product, okay, so the compound ends up with less energy because the changes in enthalpy delta H are negative. Okay, so energy is going out of this reaction. That means the compound ends up at a lower energy state. So energy is leaving exothermic the compound. Okay, so that's a more stable state for it to be in right there. Okay, 6. Why is the enthalpy of H2o liquid a more negative value, negative 285.8 kilojoules, than H2o gas at negative 241? Okay, so what that means is that more energy went out of the liquid water than out of the gaseous water, the gas water, which is water vapor. And that makes sense. Liquid water is at a lower energy state. Its molecules have less energy. They come together, they stick together, intermolecular forces, they stick together, and they have less energy than water vapor, which is steam. So they have less energy means that more energy had to go out. When you created the water, more energy had to go out of the water so that it would be at a lower energy state. Not as much energy went out, only negative 241 went out of water vapor. And therefore it still has more energy. It has, if you take the difference between these two numbers, it has about 44 kilojoules more energy than does liquid water. And that's why it has more energy. That allows it to remain as vapor. The molecules stay apart from each other. They have enough energy to pull apart from each other, and so it stays at water vapor. So let me say it again. More energy went out of the liquid water. That made the molecules less energetic, so they came together and they stuck together as a liquid. Less energy came out, 44 joules less energy came out here than here. That means those 44 joules of energy are still inside the water, and that's what gives them the energy to be a vapor, to push apart from each other and to form water vapor. Okay, so we'll go ahead and write that. Okay, so more energy, negative 285.8, exited the liquid water than exited the vapor, which was only negative 241, which means that the liquid water, has lower energy than water vapor, which is a gas. The difference of about 44 kilojoules that remains in the water vapor allows the molecules to have enough energy to separate into vapor. By the way, a term that you learned in intermolecular forces this week was heat of vaporization, or enthalpy of vaporization. That difference of those roughly 44 kilojoules between these two numbers is the enthalpy of vaporization. It's how much energy it takes to turn liquid water into water vapor. That's the enthalpy of vaporization for that. Okay? Okay, so the first of the three methods we're going to study is the enthalpy of formation method. It's actually kind of a short, quick method. It's not so bad. So what I'm going to do before I do that, I said I was going to make you do these, but we're going to need these to do this, so I'm going to go ahead and do them for you. How about that, okay? So this is going to be H2 gas, and this should have been gas over here. We're at a point in writing chemical equations where we do want to write the state of matter: gas, liquid, solid, or aqueous solution. Again, I'll use a capital L. Because lowercase is hard to read, but it's not L, it's gas. This one we are doing. So this was L, this is gas. Okay, so again, we just answered the question, why are these two numbers different? Because to make it a liquid, you had to take more energy out. If you leave it as a gas, the gas still has more energy left inside of it, the water vapor, and so it's a lower number. You don't take as much energy out of it. All right. And then these two down here, I think you can do these. You're going to need 8 hydrogen, so that's going to be 4 H2. And finally, this is butane. And you need 10 hydrogen, so it's going to be 5 H2. Okay, so you're going to need these. So we went ahead and filled these out. Okay, so let's go ahead now and do this. So here's the formula. Using the heat enthalpy of formation method, write the formula for enthalpy of formation. Delta HFS. So there it is. So the delta A of reaction, and that's really heat of formation of this type of reaction, is the summation, that's the summation sign, the number of moles times the heat of formation of the products. The circle means at standard state conditions, which is 1 atmosphere. It's not the same as STP. STP is 1 atmosphere and 0 degrees. Standard state is 1 atmosphere. The temperature doesn't have to be anything in particular, but usually we think of it as being 25 degrees centigrade, which is just about room temperature. So 0 degrees is freezing of point of water. 25 degrees is about the temperature in the room on a typical day, in your room on a typical day, okay? All right, so it's the number of moles times the heat of formation of the products, and then you subtract from that the summation. So a lot of times I like to put big square brackets around this to be sure you don't get these confused. That's my choice. It's the summation, number of moles, times the enthalpy of formation of the reactants. All right? Now, what is the enthalpy of formation of any pure element in its standard state? I do want to refer you back to the notes on this. You should be reading the notes on this. It does give sample problems and it answers questions like that. I'm going to go ahead and answer this question though, okay? So what is the enthalpy heat of formation? Okay, so complete sentence answer. It's 0. So what are we talking about? Pure element state. We would be talking about O2, for example. We would be talking about carbon. We would be talking about H2 by itself. Those are 0. All right? Okay, and I should correct this. It really should be delta H of F, enthalpy of formation. It is a reaction, that's true. Generically, it's a reaction, but it is the heat of formation specifically. Okay, let's do some of these and it'll make more sense. So using the enthalpy of formations in the table below, so I've given you what you're going to need here. Find the enthalpy of the reaction for this reaction. So 2NO plus O2 gives you 2NO2. I really like you anytime you do a problem. I know you're going to hate this. I'd like you to write the formula out. Then you end up committing the formulas to memory. Alright, they don't give you all the formulas on the AP exam. So I'm going to write out this formula. It is a little time consuming, but no gain without pain, right? So I'm going to change that to formation. I can put the little circle there, standard. Okay, so one thing you're going to have to do is the chemical equation, reactants on the left, products on the right, like any chemical equation. But you notice here you're going to have to flip it around to do the math. You're going to have to take the enthalpy of formation of this and put it over on the left-hand side, and the enthalpy of formation of this, put it over on the right-hand side with the subtraction sign. So let's go ahead and do that. So it's going to be 2 times the enthalpy of formation of NO2, which is this. So it's going to be 2. That's the only thing we have on the product side. Okay, and then it's minus the enthalpy of formation of NO, nitric oxide, and that's this. And it is 2 moles, so you always have to include the moles. Okay, and then inside of this you have to add the other reactant. But what did we just say? A pure element has an enthalpy of formation of 0. Just go ahead and write it anyway. Don't skip it. It just emphasizes that there is an enthalpy, that you did include that. It just happens to be 0. Okay? Alright, so now you can do the math on this. And what we get for this is that the enthalpy of formation of this is negative. Most of the time it is negative to form a new product. Goes to a lower energy state, kilojoules. The units of measure in these problems are always kilojoules. Okay, so there's the answer for that. So you can see this really wasn't that hard. It's just some arithmetic to do this. Okay? Alright, let's do another one. Okay, let's get rid of that. Okay, this is already a balanced equation. I believe I balanced all the equations in this assignment. Okay, so let's do the enthalpy of formation use the enthalpy of formation for methane. You're not finding the enthalpy of formation, you're using the enthalpies of formation to find out how much heat, how many kilojoules come out of this reaction. Okay, so let's be clear what we're talking about, alright? So let's go ahead and write the formula. Can you do it from memory yet? Okay, there it is. So what we're going to have to do is take these two on the product side for carbon dioxide and water and put them over here, and then put a minus sign in there, and then take these two on the reactant side and put them over here. Simply because that's the way the formula does it. Products minus reactants. Okay, so let's start doing that. So what you're going to need now, you notice I didn't give you the value, so you're going to have to come back to this table. So first one is carbon dioxide. There's 1 mole of that. I'm going to write the 1 even though you don't have to, just to emphasize that you always want to multiply by the number of moles, which is 1. And we come back here, and for carbon dioxide, we see that it's negative 393.5. Okay, now inside here it says summation. That means you're going to add. So the next one you're going to add. Watch out for your negative signs. You're going to get all tied in knots with negative signs here if you're not careful. Okay, it's 2 moles of water, so it's 2, and it says specifically, I didn't say what kind of water. That was bad of me. I'm going to say it's liquid water, gaseous water. Let's say gaseous. Okay, so that you have to know that to do this problem. If I didn't leave it, you could have just picked whichever one you want. Okay, but I should have put it there. Okay, so we go to gaseous water. That's water vapor. It's right there. And it's going to be negative 241.8. Now we go over to the reactant side. We do the subtraction. We go over here. For CH4, we have that right here. And it's negative 74.8. And it's only 1 mole, so I should put a 1 out in front. Right there. And then it's a summation. That means you're adding. And what are you adding? 2 of O2. So that's going to be 2 times what? What number for O2? A big old 0. Okay, that's an element in its natural state. A pure element in its natural state has no enthalpy of formation. Okay? All right. Okay, so here we go. You got to watch out. Don't get twisted around on your negative signs here. I would do these this side and then this side. Okay, so, and for this side right here, the product side, I get negative 877.1 kilojoules. Now let's do this side. Well, that's pretty easy. It's negative 1 times that and then 0, so it's going to be negative 74.8. Again, keep them in the square brackets like that, because now you have a minus sign right here, so it's going to be minus a negative is going to turn it into a plus sign. Okay? And what we get for that is, again, knowing how to do the problem and doing it accurately and correctly are two different things. You got to really be careful with the negative signs here, okay? Got negative signs all over the place, and it can be very easy to get one turned around and not do it right. So I would just do it in pieces. Do this, put them and keep them in the square brackets, put the minus sign in between them, and go ahead and solve. Okay, let's keep going. I'm not going to do all of these, but I think I have 3 more. Okay. I'm going to do one more. Now this one you can do from this table here. But this one you can't. We don't have that. We have everything except this. So where do we find it? Okay, so where you would find this, because it's not one that we figured out earlier, is you go to your textbook, and in the back there's an appendix. Try to crowd it in here. It's Appendix C, right there, way in the back of the book. And those appendices have a lot of information in them that you can use. And I'm going to see if I can get the camera over this. There we go. And the compound was C2H5OH liquid. And there it is. There's the delta H of formation in kilojoules per mole is right there. So it's negative 277.7. So that's where you would find that number. Okay, so we'll come back here. Let's go ahead and write that down. And since it is 1 mole here, it's that much per mole, but there is 1 mole here, so that's how many kilojoules we have for this reaction. If it was more than 1 mole, we would have to multiply that, okay? All right, okay, so let's go ahead now and do this. Again, write out the equation. Again, let's just review how to read that. It's the summation of all of the delta formation of reaction of all of the products, and for each one you have to multiply them by the number of moles. So in this case 2 moles, in this case 3 moles. Okay? Okay, so let's get started. So over here we have 2 CO2. Come back here to our page 1, and CO2 is negative 393.5, and we have 2 moles of that. Then it's plus this, and it's water in liquid form. So right there, water in liquid form is negative 285.8. Big square brackets around that whole thing, and then a negative sign. And then we have our new compound here, which is this. There's 1 mole of it. Okay. Plus the oxygen is 3 times 0. Pure element. Okay, here goes the fun part. Be careful of the negative signs and go ahead and compute this. Okay, and for this part right here, I'm not getting particular about significant figures here. And for this part right here, it is minus, put my square brackets around everything, minus negative . Okay, that's going to be a plus, so this minus negative becomes a plus, so this plus 277. And that gives us, for this reaction, kilojoules. Okay. All right. So I'm going to leave you with the last two to do on your own. This one you can do entirely from this table right here. This one, you have hydrobromic acid here. And that is, you come to Appendix C. It's a little cumbersome to put this in front of the camera. And you find hydrogen. Actually, you don't. You go to bromine. My bad. Okay, and there it is. HBr, hydrobromic acid, is negative 36.23. I'll be nice and I'll just write it down for you right here. Remember, you still have to multiply by the 4 moles. Okay, so that's hydrogen. And then the rest of them you can get, oh, bromine. Well, bromine. What about bromine? Okay, pure element. That's a diatomic molecule in its most, so it's in its most stable form. I'm not sure, and bromine, interestingly, is a liquid. It's a diatomic molecule, but it is a liquid at room temperature, so that is its most stable form. Anyway, that means, is this going to be 0? This is going to be 0. So that makes it a much easier problem. Okay, and then as I said, the one above, you can do that one entirely from the table in the front. So go ahead and finish those up. I'm going to end this part of the video now and continue with Hess's law and bond energies on a different video. Okay? So go ahead and finish out these problems.